My cat is being very noisy. They always pick the time right when I've got 10 things going on to decide, hey, I really want to eat now.
My cats at like 1 o'clock in the morning search the whole house for socks, and then they find the socks and carrying them around and meowing. It's awful.
Okay, so everybody got exam 2 back yesterday or earlier. Any questions about anything from exam 2? I'm going to have you do a very similar thing to what you did for exam 1 in order to earn your curve for exam 2. So if there are questions that you want to get over or go over, now is the time. Everybody remembers how to view their feedback. So, okay. Meadow, are you there? I just see the still
Yeah,
picture.
I'm here.
Okay.
I was wondering if you could go over the first redox reactions one.
Yeah, absolutely. As a matter of fact, for some reason, redox, like people got just screwed by that one on this test, and I don't know what happened. So I thought I explained it well.
Yeah, a redox reaction on one of the quizzes.
You're talking about number 11?
Yeah, there might have been a redox reactions.
I'm not talking about the quizzes. I'm talking about on the test. Are you talking about question number 11? How about
I am, yeah.
Oh, okay. So I can screen share. Yeah, this is what I've been doing today. No, stop. Stop. Where's the go the F away button? All right. I've had committee meetings all day today. Brutal. You think exam 2 was bad? Try sitting in on the assessment committee meeting. Oh my gosh. Okay, but that's why they pay me the big bucks. Huh. All right, so which of these statements, first of all, Meadow, we have to read carefully because we're looking for one of the statements that is false, right? There are actually 3 of the 4 of them are true, only one of them is false. So in order for us to figure out if these statements are true or false, if we read them, they all have something to do with oxidation and reduction. So we got to figure out what's going on in terms of the things that are oxidized and reduced in this reaction. Then we should be able to intelligently address A through D here. All right, so let's do it. So first of all, let's figure out what atom is oxidized, what atom's reduced, what thing is the oxidizing agent, what thing's the reducing agent. And from there, we'll evaluate the veracity of these statements, the truth of these statements. Okay, so anytime we have a metal that has no charge and is all by itself, in any atom that's all by itself without any other atoms around, unless it has a charge indicated, we assume its charge is going to be 0. So that copper has a charge of 0. Mm-hmm. This tin is part of a compound with 2 oxygens. We know that oxygen in an ionic compound has a charge of -2 because it's a group 6 nonmetal. And because those 2 oxygens each have a -2 charge, that must mean that tin is a +4 here. In the products, now our copper is in a compound with oxygen. Since oxygen, as a nonmetal, has a -2 charge when it's part of ionic compounds, that means that that copper has to be a +2 in order to get the charges to balance. The same thing is true here with tin. Now it's with just one oxygen. So if oxygen is a -2, then the tin in the products has to be a +2. So which atom is oxidized? It looks like copper starts out as a 0 and it ends as a +2. It looks like tin is reduced. It starts as a +4 and ends as a +2. I'm losing my voice a little bit. Give me a second. If copper was oxidized, then SnO2 must have been the thing that caused the oxidation. So SnO2 here would be the oxidizing agent, and Cu would be the thing that caused the tin to be reduced. So Cu is the reducing agent. Okay. Now, A, copper is the reducing agent in this reaction. That's a true statement. All right, that's not the one we're looking for. We're looking for the falsehood here. B, tin is reduced in this reaction. Well, tin starts as a +4, ends as a +2. That's a true statement as well. C, tin has a charge of +4 in the products of this reaction. In the products of the reaction, tin has a +2 charge. That is the liar. That's the false statement. And oxygen is not oxidized nor reduced in this reaction. It starts as a -2, it ends as a -2. It is not oxidized or reduced in this reaction. So that's a true statement.
Gotcha, that makes sense. I think I tripped up where seeing that Cu had a 0 charge. I think I added a charge to that.
Yeah, I mean, you can't just add charges willy-nilly. If that Cu already had a +1 above it, we would know it was a +1, but it doesn't, right? So whenever an atom is by itself, if there are no other atoms around, or even if it's a pair of the atoms together, like O2, if there are no other atoms around, if it's not part of a compound, unless there's a charge indicated, we assume that the charge of those atoms is 0.
Gotcha, that makes sense.
Other questions from the exam? So yeah, like in general, the redox questions were pretty poorly answered compared to other classes. So something went haywire in our presentation of redox chemistry this time. I don't know what happened.
I was just looking at mine, and because I just seen the test right before we got online, and I actually studied that all weekend so I could have some sort of an idea of what to do, because I was tripping up over that I think a lot during the week, and I did okay for those questions.
And you know, the other option is if you're struggling on a topic, you could always, text the instructor who gave you his cell phone number and say, I'm struggling with this. Can we hop on office hours for 10 minutes and do an example together? Right? That's a possibility. Very few students are availing themselves of the fact that I am willing to help them if they're struggle busing. So you got to let me know if you're struggling. Now, after the test, I know that students should have spent more time with practice on redox reactions. I would have been happy to provide that practice if I had known, but nobody said anything.
Dr. Musk?
Reed, what can I help you with?
Yes, I did. It's just exactly 4 plus minus 2 plus. My thinking, Cu plus 2 or minus 2. I did, right? But actually, why it's false statement that Sn has a charge of +4 in the products of this reaction?
Well, what is the charge of tin in the products of the reaction? Right there, there's tin in the products. It has a charge of +2. That's not the same as +4, so that's a false statement.
Oh, okay. So 4 is this side, but that's why to reduce. So,
This is the product.
mhm. So, okay, that is product. Okay.
This
So
is the
then-
reactant.
Okay, so Y tin is the not the reduce agent then, the +4 to gain lose +2 seems like 4 to 2.
Yeah. So tin was reduced in this reaction.
10 reduced, right? Okay, yeah, okay. That's right.
Uh,
Oh,
Other-
little bit I confused. Okay, thank
that's
you.
okay.
Yeah, okay,
Other questions?
yeah. No, yeah, because the thinking like a those are I did, but actually the answer was wrong. Oh my goodness. Okay.
Yeah, I can't grade your work on a multiple choice question. I only grade what answer you pick. That's it. So either you pick the one you're supposed to or not. I can't do any more than that.
I know.
Other questions? I know not everybody that's in the section right now got 100% on the exam. So maybe you see your mistake and you already realize what you did wrong and can fix it. But if there's something that you're bewildered by and want to go over, I'm here. I'm happy to go over it.
I'm looking at my test right now.
Sure. Yeah, I don't expect you to, I mean, take a second, look over it. It's fine. If we were in class together, that's the first thing that I would do at the beginning of the class today is hand back the exams and be like, here you go, take a look. Are there any questions that you want to talk about? Meadow, the me too was, I'm still going over my test. Is that right?
Yeah, that's right. Sorry.
Okay. No, it's fine. Why are you apologizing? You didn't do anything wrong. Class average on this exam was pretty darn good. There were a lot of very, very good scores. A lot of scores in the like mid to high 70s and into the 80s. So 81 or higher is an A grade on the exam. So if you got a score of 81 or higher, you get your exam curve for free. And there were a number of those, which is fantastic. So I was pretty pleased. And there were some people that need to do better, and they're going to be able to do test corrections to earn some of those points back. It's not going to be quite as generous as the curve for exam 1, because I can't be that generous on 3 exams, or it just defeats the whole purpose of having exams at all. But there will be a curve.
So I looked at my test and I think I know what I did. Some of it was because I worked a little slow and so I was rushed, but I'm happy with my grade. But I think I'll go back through and correct
That's
what
fine.
I
Yeah.
missed.
So the big, if you can identify what you did wrong and you can correct it given enough time and like the lack of time pressure, then that's not what we need to talk about here. It's just if there was a question that took you by surprise and you have no idea what you're doing or how to even approach it when you start talking, to go back through and do your principal correction, that's what we need to talk about now, because I got to at least give you a starting place for thinking through it if you're completely lost.
So I got 10 wrong, and I am a little bit confused about where I went wrong on that one.
Okay. Yeah.
Or how I
so
got a
let's
wrong
talk about
answer.
it. So this is 2 skills. We have to be able to turn a name into a formula. And then we have to be able to turn a formula into a molar mass. All right. So diboron tetrahydride, that name refers to what compound? Meadow, can you tell me what the compound is we're talking about here? So di, the prefix di means.
Well, I just have the caramel by the coffee.
What's that?
Renee, was that you talking about caramel and coffee? That sounds delicious.
Oh, I'm so sorry.
No, it's totally fine.
Okay, so is dyes 2? Gosh, I forget. Yeah, dyes 2.
All right, so that's the first part, is we got to figure out what compound we're talking about here. So diboron means there are 2 borons in this compound. What about the prefix tetra?
That's gonna be 4.
Right. Hydride, what atom are we referring to when we're talking about hydride?
Hydrogen and it's just is it just
That's it.
hydrogen? Yeah.
Hydrogen. So B2H4 is the formula that we have to find the molar mass of. And molar mass is what we get by adding all the masses of the atoms in that formula on the periodic table. So I have 2 borons that are each 10.81. And 4 hydrogens that are each 1.01. If you used your Alex periodic table, they would have one more significant figure for those molar masses, but who cares about that?
Yeah.
So if you add all those together, the answer that I'm getting, 25.66.
Oh, gotcha. Oh, how did I get that big of a number? I got like 163
I saw that answer from
4.43.
several people, and I have no idea because they didn't show their work. So if you had showed your work, then I could have at least like understood where you were coming from. But if I just got a number, it's either right or it's not, and I can't give partial credit, right?
Yeah.
So anyway, that's what the reasoning is. You have to be able to use what you know about how binary covalent compounds are named to turn this name into a formula. And then you have to know how to calculate the molar mass of a chemical formula after that.
Gotcha. I must have just, I don't know, done the prefixes wrong. Or yeah, I might have thought tetra was a lot more than it is.
Other questions? So if there aren't any other questions, the way that we're going to do exam 2 corrections is exactly the same way that we did exam 1 corrections. For each question that you missed, you have to tell me not only the correct answer to the question, but you also have to explain the principle that leads you to the correct answer. In other words, tell me how to get to the correct answer. Don't just give me the correct answer. So you have to explain the thought process that leads to the right answer for each one that you missed. That's the best way that we can train to not focus so much on the end product, the answer, and instead focus on the principles, the process. So in the end, I can always ask questions a slightly different way, but the principles that we're learning in class, those are the same that we apply over and over again to every problem. So if we spend our time focusing on those, that's how we're going to end up doing really, really well on this course.
Thank you so much for offering that. I definitely get, I remember doing it like last test and I definitely understood everything a lot better by going through those corrections.
Good, I'm glad. That's the whole point of them. I can't even remember anymore when I started doing that, but it was pretty early in my teaching career and it's like one of the things that's worked out pretty well. So I think I started it in my 2nd year of my first job, which was, it's a few years ago at this point. I think that 2nd year was like 2008 at this point. At least the 2nd year of like my full-time teaching. So yeah, I haven't held on to many of the things that I've done in the classroom for that long, but this one has legs. It seemed to work out pretty well. I will put a due date on Canvas for the exam 2 corrections box. So today's Friday. Why don't we make the corrections due a week from today? I know that's the day after Thanksgiving, but I mean, who cares? You got a whole week. You can do them ahead of time if you want to, but I'll make them do a week from now.
Dr. Musk.
Who's this?
Brandon.
Hi, Brandon.
I just have a question about the ALEX homework. So chapter 6 is due tomorrow. Is that right?
No, I'll extend it. So we haven't finished
okay.
talking about chapter 6, which it would be like, it'd be a jerk move for me to make chapter 6 of Alex do before we were even done talking about it together.
Okay, yeah.
Good point. We should finish almost all of chapter 6 tonight. We've gotten 2/3 of it done in recitations, but I haven't had time to process all those videos yet. They take time to process. So I'm hoping to have time to get those posted tonight. If we finish chapter 6, let's say we finish chapter 6 Monday, I'll extend it to where you at least have a few days after we finish the chapter before the Alex homework is due.
All right, that sounds good.
Okay.
Thank you.
Absolutely. Yeah, in general, you can always assume that I'm going to be fair with extending deadlines. If we haven't finished covering something in class, it's not going to be due before we've even covered it together. That would be a jerk move. And generally, I'm not a jerk. But I assure you that in this specific instance, I also will not be a jerk. So unless there are any more questions about exam 2, I would like to move on and talk about the second half of chapter 6. We've already done a couple of lessons on the first half of chapter 6 in recitations. And if you didn't catch those, I haven't got the videos up yet. They'll be up soon. So there's no need for us to go back over those because you've already got the topical videos on those sections. And there are also like 2 recitations where we've covered material from them as well. So you should be able to watch and catch up with the first half as soon as those recitation videos are posted. The second half of chapter 6, the equilibrium half, if you didn't catch recitations from earlier in the week, I honestly feel like a better way to arrange the textbook would have been to give the first and second halves of chapter 6 their own separate chapters. The concepts are somewhat related, energy and equilibrium, but tying together exactly how they're related is way beyond where we need to be in terms of math for this class. It makes more sense at our level to just treat them as separate topics, even though they are very closely related. So let's talk a little bit about the second half of chapter 6. So that starts in section 6.5. And before we get to what the book has to say about this topic of equilibrium, I'm interested in the contexts that you guys have heard that word discussed in before. When you hear about equilibrium, what does that mean to you?
Balance?
Yeah. So a synonym for balance, that's a very, very common place that you might have heard of or have an association with this term equilibrium. And in reality, it's actually a perfect translation to the way that we regard equilibrium in terms of chemical reactions. All right. So sorry about the dead air time. It's just taking me a second to write this sentence. So how do we translate this idea of balance into the world of chemistry? When we talk about equilibrium or balance in the world of chemistry, what we really mean is a balance between the reactants and products in a chemical reaction. And that's only true for reactions that are reversible reactions. In other words, reactions where the products of the reaction can react and turn back into the reactants. So the reaction can go in either direction. So here is an example of that kind of reaction. Note that the reaction arrow is special for equilibrium reactions. You see a forward arrow and a reverse arrow. That's what denotes that reaction being an equilibrium reaction. So when you see an equilibrium arrow in a chemical reaction, you know that that reaction is reversible. In other words, the products can turn back into reactants. And in general, we define equilibrium as the point in a reaction at which the forward reaction is going just as fast as the reverse reaction. So if that doesn't resonate to you, here's another way of explaining that same concept. That's my co-teacher, Oscar. So another way of explaining this is the reactants are being turned into products at exactly the same speed as the products are being turned back into reactants. That's what we mean by an equilibrium state. All right. So this is often referred to as a dynamic equilibrium. Remember, the word dynamic means moving or in motion. So equilibrium is not a point at which a reaction stops. Equilibrium reactions are always occurring in both directions. It's just that the concentrations of the reactants and products stop changing after a while when we get to a place where the forward reaction is going at the exact same speed as the reverse reaction is. If the two reactions are going at the same speed, then the amount of CO2, the concentration of CO2 is not going to be changing any longer because we're making new CO2 at exactly the same speed as we're using up CO2 to make reactants. So an important thing for us to realize in our discussion of equilibrium is that every individual chemical reaction that is an equilibrium reaction has its own balance point, all right? What that means is that some reactions are in balance where there are a lot more products than there are reactants. Other reactions have a balance where there are a lot more reactants than there are products. Renee, are you trying to talk to me? You're muted.
No, thank you though. I'm multitasking.
Okay, that's totally fine. Just although you looked like you were looking right at the camera and saying something.
Oh,
So I wanted to make sure I was getting it.
taking notes and talking at the same time.
That's fine. So this is an equilibrium reaction. That highly favors products at equilibrium. So the balance point in this reaction is a point at which we have a lot more products and very, very few reactants at equilibrium. All right. We'll talk more mathematically about that in a minute. There are other reactions that are the exact opposite. As a matter of fact, here, a very similar reaction. These happen to be reactions of acids with water. So in these two examples, in the first example, this balance point is tilted very much in favor of products. So if we let this reaction come to equilibrium, we're going to have almost all products and almost no reactants at equilibrium. In this second reaction, it turns out that the reactants are highly favored at equilibrium. So if we have this reaction and let it come to equilibrium, let it go to its natural balance point, at that balance point, we will have almost all reactants and almost no products at equilibrium. Very different balance points. So every reaction has its own balance point. Some of them highly favor products, some of them highly favor reactants, and some of them have a significant amount of both reactants and products present at equilibrium. So because every reaction has its own balance point, chemists came up with a really cool way of describing that balance point mathematically. So we describe the balance point mathematically with this thing called an equilibrium constant. So I'll define that on the next page where I have a little bit more space. I want to make sure that you guys have time to get the notes. Has everybody got everything here? Can I move on, or I know my hand's in the way? So an equilibrium constant is a number that describes the ratio of products to reactants of a reaction at equilibrium. And normally for the equilibrium constant, we give it the variable K. So depending on the book you're using, the equilibrium constant may be listed as a K sub C, all right? So C referring to concentrations of reactants and products, or K sub EQ, as in a constant that has to do with equilibrium. There can also be some specific versions of these constants, but any equilibrium constant K is talking about a ratio of products over reactants, always. So how do we calculate K for a chemical reaction? How can we find what the balance point is for a chemical reaction? Now imagine this is sort of a hard thing to think about, but we're going to try anyway. This is a reaction that's at equilibrium. Those should all be B's. The lowercase letters are the coefficients in the balanced equation. So if we are to define what K is mathematically, the K for any reaction, remember it's a ratio of products over reactants. So what we're going to do is we're going to take the molar concentration of product C and raise it to the coefficient little c. So in other words, whatever the number is for our coefficient becomes the exponent in the equilibrium constant. We're going to multiply that by the molar concentration of D raised to the coefficient's exponent. So those are our products, and here are our reactants. So those should go in the denominator. So reactant A is going to be raised to the little a power. So if there were two of those A's, then A would be squared here. Reactant B is going to be raised to the little b power. So this may look stupid right now. I'm going to give you examples. It's actually really easy once we apply it. This is just a general formula, okay? So it also works for things where there's only one reactant. If there was only one reactant, let's say that there was just two A's in the reaction, in the reactants, then we would just have A squared in the denominator. There wouldn't be any second reactant in the denominator at all. So how would we translate this general formula for us calculating the ratio of products over reactants into a form of the equilibrium constant for a real reaction? All right, let's use the example that we had from the previous page. If I can get back to it. So if we had this reaction and we were trying to write the equilibrium constant for this reaction, K sub C or K sub EQ, depending on what textbook you're looking at. what we would do is we would take the molar concentration. So whenever we put something in brackets like this, that means we're talking about a molar concentration of it. So our molar concentration of CO2, and we're going to have to raise that to the same power as our coefficient. So if there's no coefficient, how many CO2s are there? How many CO2s are there in this reaction?
1.
Right. So CO2 to the first power means that we don't actually have to write the power in because that's just CO2. And then we're going to multiply that by H2 raised to the first power because there's only one H2 in there. So those are our products. We're going to divide that by our concentrations of our reactants raised to the powers that their coefficients tell us. So carbon monoxide to the first power times H2O to the first power. Note that H2O is a gas here. That's really important. The reason why it's important is because the only things that end up mattering in terms of an equilibrium expression So when we're writing equilibrium expressions, the only things that end up showing up in those mathematical expressions from the reaction are gases or aqueous things. Solids and liquids don't show up. So if there were a solid or liquid in here, it wouldn't be part of the equilibrium expression. We would just leave it out. So let's look at another example from a previous page. If we look at this equilibrium reaction and try and write a K, an equilibrium expression for it. I'm going to call this a K sub A because this happens to be the reaction of an acid with water. It's a special kind of K. We calculate it the exact same way that we would calculate any equilibrium constant, products over reactants. So here we have one H3O plus and one Cl minus. Those products go in the numerator. And we have HCl aqueous and H2O liquid as our reactants. Remember that liquids and solids don't show up in the equilibrium expression. So this aqueous HCl is the only thing that ends up in the denominator here. People with long hair, have you ever just like completely inhaled your hair before? Has that happened to you? That just happened to me. It's the first time that's ever happened. That was really gross. You guys almost just saw me throw up. It was really close. Let's do
I think it's
another one
worse when it
together.
gets in your eyes.
Ugh.
Don't eat hair, Dr. Musk. It's bad.
I wasn't eating it. I was trying to inhale it. Apparently my lungs wanted some hair for some reason.
You have a powerful inhale.
It's from my former career as an opera singer.
Give us a tune, please.
I said former for a reason. I've lost my strong head voice, Andrew. If I have to sing now, it would be as a baritone, and I would rather die than become a baritone when I used to be a tenor.
Well, all the theaters are closing down, so you're going to have to come out of retirement. We need somebody up on stage.
They're actually doing like remote performances with people in their living rooms. Like all the cast members just get together and do Zoom performances of things. It's kind of awesome.
Really?
Yeah.
Pretty cool.
So if we wanted to figure out our equilibrium constant for this reaction, finally we have something where we have a non-1 coefficient. Remember, it's always a ratio of products divided by reactants. So it would be our concentration of NO squared. The coefficients from the reaction become the exponents in the equilibrium expression. And then N2 times O2. So those are all molar concentrations. If we knew what the concentrations of our reactants and products were at equilibrium, we could calculate our equilibrium constant, our ratio between products and reactants.
Quick question. Isn't that just 1?
What do you mean?
Well, I mean, like, because, like, it's the same, like, if you were to combine that, like, wouldn't that be, like, 1?
So let me give you some data, all right? This is a mathematical expression. It doesn't tell us what the ratio of products over reactants in this reaction are. In fact, it would probably be something like so if we know those concentrations, calculate the KEQ for this reaction. It's just a number. And for reasons that we're not going to talk about in this class, when we report KEQs, even though we're putting in numbers that have units attached to them, molarities, leave the units out and just use the number part. All right. We're always going to input molar concentrations, but just put the number part in when we're calculating K. So we want K to always end up being unitless. It should have no units whatsoever in it. So just put the number part of the molar concentrations in when you're calculating your K. I'm calculating a K of 1.11 times 10 to the minus 6. you guys get the same thing?
Working on it.
So that's all right. I got that by inputting my equilibrium concentration of NO, 2.15 times 10 to the minus 6 molar, squared, because this is the expression that tells us about that ratio between products and reactants. And then my N2 concentration at equilibrium was 0.00354 molar. My O2 concentration at equilibrium was 0.00118 molar. And then I put that into my calculator to solve. And that's what I got. So importantly, now that we have solved for K, this number K, what does it tell us about the balance between reactants and products? First of all, is that number a big number or a small number, the K that we calculated? Yeah, Andrew's holding up fingers like this. Yeah, it's really tiny, okay? So not in scientific notation. That's what my number represents, not in scientific notation. It's really tiny. So if that is a ratio between products and reactants, so if that number is our ratio of products over reactants, what do we have a lot more of at equilibrium for this particular reaction? Do we have a lot more reactants or do we have a lot more products?
Reactants.
Yeah, if we had a lot more products than we did reactants, then our K would be a really big number. In this case, it's a really tiny number, and you can see that at equilibrium, our concentrations of reactants are a lot bigger than our concentrations of products. All right, so that's what the equilibrium constant tells us. Whenever we have a very small equilibrium constant, small K, that means we have a lot more reactants than we do products present at equilibrium. If K is a really, really big number, then that means that at equilibrium, products are favored over reactants. We have a lot more products than we do reactants at equilibrium. And if we have a K that is not super duper small or super duper big, the exact numbers aren't that important, but anything relatively close to 1, that means that we're going to have significant amounts of both reactants and products present at equilibrium.
Is that supposed to be 1.00 or is that supposed to be 100?
That's 100.
Okay.
So think about K being 100 means that our ratio of products to reactants is 100 to 1. So roughly 100 times as many products as there are reactants. A K of 0.01 means that we have 100 times as many reactants as we do products. Does that make sense? So anywhere in that range, in between those, we have a significant amount of both reactants and products at equilibrium. Any questions about that so far? Let's do another calculation of an equilibrium constant together.
Do chemists tend to look at things in equilibrium a lot?
Oh yeah, this is an absolutely crucial concept. So especially when we get to the second part of our equilibrium discussion, which is how we can shift the equilibrium for a reaction. That's called Le Chatelier's principle, if you've read ahead in the textbook already. So Le Chatelier's principle is really important because it gives us a sort of toolkit that we can use to maximize our yield of products when we're trying to get a reaction to run better. And lots of reactions are equilibrium reactions. They're never going to go all the way to completion, 100% to completion. So our job is to sort of tailor the reaction conditions to push them to make as many products as possible. And we have to use what we know about equilibrium reactions to make that happen.
Can that be used in reverse? So let's say we wanted more reactants. Could it be used the other way for like?
Yeah, absolutely. Absolutely. So really in an equilibrium reaction, Andrew, reactants and products are an arbitrary construct. We just refer to the reactants as whatever's on the left-hand side. But those reactions can go in either direction.
Gotcha.
So let me give you guys another example and we'll calculate. Oh, that's a really big exponent. I can't decide on the example that I want. Let's just do this. It'll be fine. Let's not let the perfect become the enemy of the good here.
I'm getting 4.
Yep. So Andrew, what does that tell you about this reaction? Where does the balance point lie for this particular reaction?
It's significant amounts of products and reactants because it's between the 0.01 and 100.
Which do we have more of, products or reactants?
The product.
Yeah, if it's the ratio of products over reactants, then we know that a ratio of 4 to 1 favors products as opposed to reactants. It's not heavily favored. There's a significant amount of both, but it favors products. So based on just the size of that equilibrium constant, we can tell where the balance point is for that chemical reaction, whether it favors products or whether it favors reactants. I'm trying to find you guys a little bit harder equilibrium reaction to write an equilibrium constant for. Our books
It's all
examples are all too easy.
Just kidding.
What's that now?
I was like, it's all good. We don't need anything harder. Just kidding.
No, we do. We definitely do. So see if you can write me the general expression for the equilibrium constant for this reaction. So how would we calculate K for this reaction? You don't have to actually calculate it because you don't have the concentrations, but what would the expression look like to calculate K for this reaction? Products over reactants. The coefficients from the balanced equation become the exponents in the equilibrium expression. So my concentration of NO is going to be raised to the second power. My concentration of Br2 will be raised to the first power. And in the reactants, the denominator, my concentration of NOBr will be raised to the second power. So that is my equilibrium expression for this reaction. It turns out that I know mathematically what the value of K is for this reaction. And it turns out that at room temperature, So when you see Ks reported, generally they will be reported with a temperature attached to them. The reason why is that number, the ratio of products to reactants, changes with temperature. So it would be a different ratio if we were talking about 100 degrees Celsius instead of 25 degrees Celsius or 20 degrees Celsius. So if we know what the concentrations of NO and Br2 are at equilibrium, and we know what the equilibrium constant is, can we solve for the equilibrium concentration of NOBr? All right, so we know that our K sub C, our ratio of products over reactants for this reaction, has a value of 0.014. That's a constant. It's something that we would have to look up for any given chemical reaction, or we could determine it experimentally if we measure the concentrations of reactants and products at equilibrium. So most of the time for us, if we're given a reaction, we'll be given a value of K as the known balance point for that reaction. So if we know the concentrations of each of our products at equilibrium, can we calculate the concentration of our reactant at equilibrium? Sure we can. We just have to substitute what we know into the equilibrium expression. All right. So 0.014 is going to be equal to our concentration of NO at equilibrium squared. So NO has a concentration of 5.4 times 10 to the minus 4 molar. And because there are two NOs in the reaction, our concentration of NO is squared times our concentration of Br2, which is 5.4 times 10 to the minus 4 molar. Divided by our concentration of NOBr squared. So all we have to do at this point to solve the problem is isolate NOBr algebraically. So can we do that? See if you can solve for NOBr from this expression for me. Or maybe it'd be easier to solve for NOBr squared, and then you can just take the square root of that number. That's fine as well. So to me, isolating this algebraically is best done by multiplying both sides of this equation by NOBr squared. So we move our NOBr over here, and then we divide both sides of the equation by 0.014. So we move our 0.014 to the denominator of the other side. Note that 5.4 times 10 to the minus 4 squared times 5.4 times 10 to the minus 4 is 5.4 times 10 to the minus 4 cubed. So I simplified that expression. From here, it's a calculator problem. So I'm not actually rounding this off here. I have the number in my calculator. So this is what I'm getting for NOBr squared. Excuse me. And from there, we take the square root. So I'm getting a molar concentration for NOBr of 1.06 times 10 to the minus 4 molar. You guys getting the same thing?
Yes.
Sweet. So that's how we use equilibrium constants. If we know all the molar concentrations of our reactants and products, we can use those to solve for the equilibrium constant. Or if we know the equilibrium constant at the beginning, we can use that with a little more information to solve for the equilibrium concentration of one of the reactants and products. So really the important thing is you should be able to write an equilibrium constant, all right? In other words, you should be able to write this general form of the equilibrium constant, and you should be able to substitute what you know into that equilibrium expression to solve for a concentration or an equilibrium constant if that's what you're solving for. This is a really important concept. It seems pretty easy, and like it is easy in some ways because equilibrium constants are just numbers. They don't have a unit attached to them at all. The size of the equilibrium constant tells us a lot about that reaction in terms of that balance point between reactants and products. So it is a pretty simple concept, but the actual way that we calculate them for a reaction that has very large coefficients, it can be pretty complex to do the math. Our last topic for chapter 6 is Le Chatelier's principle. We definitely don't have enough time to cover that in the next 8 minutes. So I think that's the point at which we're going to conclude our recitation for the day. The other thing is I have put in an extension for our lab so that the lab isn't due until not next Friday, but the Monday after that instead. So that would be the 30th of November, I think. So you've got plenty of time to work on the lab, the Boom Goes the Dynamite lab. So what we're going to do is, because you guys have exam corrections to start working on, I'm going to let you do that tonight instead of us doing our lab tutorial. There's already an old lab tutorial up. You can go through it if you want to, or if you want, we'll do a lab tutorial after class on Monday. We'll do a morning lab tutorial if anybody wants to do that. Okay. So, well, will it be morning by the time the class is over? 9 to 10. We start at 11:30. I guess it won't be morning by the time class is over. We'll do our lab tutorial after our recitation time on Monday. Okay? I know you guys are all probably chomping at the bit to start working on your exam corrections, and I don't want to hinder that at all. Remember also that if you were one of the students that studied and achieved greatly on exam 2 and got a higher score than 81 out of 90, 81 or higher, that means you got an A on the test for your raw score and you don't have to do your exam corrections. You get the curve for free. That is your reward for studying hard. So if that was you, then congratulations. And if not, then make sure you do those corrections, because that's how you're training your brain so that hopefully on exam 3, you get that raw 90% or better all by yourself. All right. It's all about getting better, improving. That's what I want from you guys.
So if you're in that category, you can't get a better grade than what you got. Is that what you're saying?
If you're in the category that got 81 or better out of 100 or out of 90.
Yeah.
No, it means that you get the curve points applied to your score automatically.
Oh, okay. Sorry.
Yeah,
I misheard.
You don't have to earn your curve. You just get it. You already earned it by getting the score that you did on the exam.
Okay.
So you'll get
Sorry.
the curve that the rest of the class gets. You just don't have to do exam corrections to get it.
Gotcha. All right.
Yeah, it's a little reward, a little thank you for the hard work. And I'm not saying that people that got under 81 didn't work hard. I know a lot of people did like really well on this exam and got, you know, scores in the high 70s. Like that's a really solid score. You don't have to get raw 90% or betters on my exams to get an A in the class. It's a pretty high bar. So if you're doing everything else that you're supposed to be doing, turning in all your Alex homework, taking any reading quizzes, although we're pretty much done with those at this point because hopefully people have gotten in the habit of watching videos and preparing for recitations. So if you are turning in quizzes and turning in Alex homework and turning in labs and not doing a terrible job on those, exams are probably going to be the lowest part of your course grade. And if you're getting in the like mid 80s on your exams and you're acing everything else, that's an A in the class. It's an achievable goal. All right. So if you're getting 90% or better for your raw score on exams, that's a really high bar. There should be some sort of reward attached. When we turn back exams in class, I often put stickers at the top of exams for students that get 90% or better for their raw scores. And I have some really flippin' awesome stickers in my office. That's one of the things that I miss the most about teaching in person is giving stickers on exams for students that get 90% or better. But anyway, I just haven't figured out a way to like paste in a sticker into the Canvas app, or else I would totally do it. And that would be really great because I could use the same sticker over and over again if I wanted to electronically.
So will you, after this is all over, will you go back to teaching in class or will you stay virtual?
I hope to God I go back to in class. Everything takes 3 times longer virtually. Yeah, I mean, I didn't sign up to be an online instructor. None of us did. We were all in class professors full time. And then the pandemic hit and we have to adapt, right? So we can't just close our doors because then I wouldn't get paid a salary and students wouldn't be able to take my classes. So we all have to do things a little bit differently for now. But let's hope. Now, I will say, Andrew, that I would not be opposed to like for a summer teaching a completely virtual section of this class. I think our virtual labs are decent enough that students that aren't chemistry majors get some exposure to lab concepts through them. And the other thing that's great is then if students are like on the go in the summer, if they're traveling, as long as they have an internet connection, they can stay connected and take the class wherever they're at. If I'm on the go and traveling in the summer, like I like to do sometimes, I can teach in the summer and make a little extra money and still be able to like travel or go visit family and things like that. So it's the fact that that we put in the effort to make the virtual versions of these courses, like it will pay off to some extent at the end. The other thing is I'll probably still have the little topical videos available on my Canvas site, even when we go back to in-person classes. What if somebody misses a class, or what if somebody wants more practice on a very specific topic? Having those little videos is like, it's a huge help, right? You can go back and watch them as many times as you want to. And why would I intentionally remove that help when I've worked so hard to create it now? So it's not just that when I go back, I'm gonna go back exactly the way things were. There are things that we've done in the prep for pandemic teaching that are gonna help all of our teaching forever for the rest of our careers when we go back to in-person. That's my optimistic view. I'm a pretty optimistic person normally.
Yeah, no. So you teach the class directly after this, right?
You mean 131?
Sure. If that's the one
directly
like,
after this, do you mean in series for like what people take after chemistry 121?
yeah, so like if
Yes.
you were going to be a science or chem major, like
So
the thing
that's different. So 121 and 131 are science classes for non-majors. That doesn't mean that they're not rigorous. It just means that like we can't spend as long covering things as they do at the majors level. So we cover lots of topics, but don't get into as much depth on things as we get at the majors level. If you're going on to majors level courses, the next majors level course you would take is the Chemistry 160 series. So 161, 162, 163. So that'd be the first year of a chemistry majors course sequence.
Would you take 131 before that, or would you just go to 160?
Go to 161. Because if you're going to be a science major anyway, the 160 series is the beginning of that pathway for chemistry majors. And in the end, the things that you would learn in 131, you're going to learn and then a bunch more in the sophomore and junior years of your chemistry major classes. Basically, I'm telling you, there's no way you could possibly be perfectly prepared for the sophomore year of majors chemistry organic chemistry is a system shock no matter how good a student you are, because it's just a huge information load. So there's no real benefit for you to take the non-majors version of that class because it's not even a 20th of the information load that the majors level is. So you're better off just jumping in with both feet and taking the majors level one.
Gotcha.
Any more questions before we're done for tonight? I don't know if Jennifer has office hours tonight, or if Jennifer, I didn't remember to write down your new set of office hours. I know you shifted some of them.
Oh, yep. I'm moving over there as soon as we're done here.
Awesome. And that gets to be a little earlier tonight. Yeah, we're just going to do the lab tutorial after recitation on Monday instead. Be a better idea, since we get till the Monday after to turn it in. Okay, if there aren't any more questions, work hard on those exam 2 corrections. And for those of you who kicked the crap out of exam 2, congratulations. I wish I could like name all of you and throw parties, but FERPA violations could cost me my career. So instead it has to be like a wink and a nod, like, yeah, you did it, awesome. I try and write messages of inspiration for lots of students on their exams, but just know that I see you. I see the hard work that you're putting in. And for the people that didn't get an A on this exam, but for example, maybe scored 50% on the first exam and scored 80 something on the second exam, I see you too. That's a huge improvement and I'm proud of you. All right. So awesome. Good work for the people that worked hard and really pulled it off. I was rooting for all of you, and a lot of people did pretty great on this exam. So feel proud of that.
I want you to know, Dr. Musk, that I've taken 2 chemistry classes before this, and I've never liked chemistry until your class.
Well, I appreciate that. Thank you.
Even though it's a virtual class and I hate virtual settings, props to you. You're a decent fucking professor. I mean, a decent professor. Sorry.
Thanks. I appreciate that. Yeah, we'll go with the PG version of that instead, but I appreciate it. I'll take it. I missed stuff in the chat. Oh, okay. It looks like all right. Just making sure I wasn't missing anything important. So definitely go and join Jennifer's study session. I'm sure that you guys might be addressing exam corrections, or perhaps talking a little bit more about equilibrium and doing some examples with that. So anyway, have a wonderful weekend, guys, because this is the last time I get to see you before then.
Okay, just don't ask me about Le Chatelier, because
I'm happy to help with that next Monday. It's a hard topic.
Kills me.
All right, have a good weekend, everybody.
All right.